In this video, we will look at present value annuities, which are different from future value annuities, although they still include those regular deposits or withdrawals. So let's take a look at this first example that I have full solutions for it just to see what a present value actually represents. So McDonald's contest has a grand prize of $1 million. However, they do not give the winner the $1 million in one lump sum. Instead, they give the winner $50,000 at the end of every year for 20 years. Well, 50,000 times 20 equals $1 million. So why don't they just give the winner the $1 million up front? Let's say interest is 6% compounded annually. Let's see how much McDonald's actually needs to invest in order to build that $1 million in the end, because realistically they're not going to have to invest $1 million. They're not actually giving $1 million of their own money to this winner. They're actually giving less than that. So let's check it out. So at the end of the first year, the winner gets $5,000 or $50,000 right here. Now that's the end goal, and they get 6% interest compounded annually. 6% is 0.06, and that is why I wrote 1.06 in the bracket. Thinking about the compound interest formula being A equals P1 plus I to the power of N, I have my future amount. Like, I know I have to give 50,000, I know the interest, and I know N. So at the end of 1 year, this principal amount grows to 50,000. And if I actually solve this, I'm just dividing both sides by 1.06. And if we think of exponent laws, when we divide by a number, if we want to bring it up into the numerator, we can just put a negative exponent. And if I plug that into my calculator, here is how much McDonald's actually had to invest at the very start so that that investment grew to 50,000 at the end of the first year. Let's look at what happens at the end of the second year. At the end of the second year, you will notice it's to the power of -2. And that's because the original equation would have been 50,000 equals the principal times 1.06 to the power of 2. And when I divide both sides by that 1.06 to the 2, it goes in the denominator. So to bring it up, I'll create that negative exponent. And here's how much they had to invest. That's even less. Let me go all the way. And actually, if you just notice, at the end of year 3, it's to the power of -3. So at the end of year 20, that last money that the winner gets, that 50,000, McDonald's only had to invest almost $16,000, and it grew to 50,000 using this calculation. So if you look at number to number here, like from here to here to here, then you will notice that each time all that we did was the exponent got smaller and smaller. And how did it do that? By multiplying by 1.06 to the power of -1, because it was smaller. So this is our common ratio. Okay, so thinking about geometric sequences again, just like with future value. Now our first term is not actually the 50,000, because if we look at our first term, this is our first term here. How did we get it? By multiplying the regular deposit by 1.06 to the -1. So this is what our first term actually ends up being. Okay, so it is more complicated than the future value, like to get the actual formula, but it applies the same geometric series information. Okay, so in the end, if we actually plug this information into the series formula, this is what McDonald's actually had to invest, around $573,000, and it grew to $1 million so that the winner gets $1 million at the end, which is wonderful. So if you compare this to future value, for future value annuities, you are depositing money every month or every year, and it grew. But with present value, you are putting money in presently, like one lump sum, and then you're taking withdrawals from it. So that's really a huge difference between future and present. Future, you're building up your account by making deposits, while present value, you're decreasing your account because you start taking withdrawals from it. So let's look at what our formula actually looks like. So here it is. After it's all simplified, in the geometric series formula, this is what it is. It looks very similar to the future value one. It's really just that numerator bracket that is slightly different. So let's apply this to a few word problems. So for our first one, Canadian astronaut Chris Hadfield has decided that he'd like to set up a bursary fund for students studying engineering at the Royal Military College. He'd like the $2,500 fund to be awarded to a deserving student twice a year for the next 15 years. If the fund earns 8.3% per annum compounded semi-annually, how much money must Chris donate today? So the question is asking how much he should put into the account today so that this student can withdraw or take away $2,500 twice a year. So the fact that the account starts with a certain amount and slowly you're withdrawing from it for this bursary, that is the clue that it is present value. So here's the key information. The regular deposits are $2,500, or in this case, they're not actually deposits, they're withdrawals. This is happening for 15 years and it's twice a year, so semi-annually, and here's our percent. So our interest per compounding period is going to be 0.083 divided by 2, which does simplify to a nice decimal, so 0.0415, and the number of compounding periods, or the number of withdrawals, 15 years, twice a year, that's 30 withdrawals in total. So let's write our present value formula. R times 1 subtract 1 plus I to the negative n, so be careful with your sign there, all over I. And now let's just plug in. R is 2,500, that's the withdrawal. 1 minus 1 plus 0.0415, and you can simplify that right away. The power of negative 30 all over 0.0415. I recommend you pause the video here and try plugging this into your calculator with full brackets, being super careful to make sure you get the right answer and you're using your calculator properly. So pause and try. So hopefully you got 42,453 and 51 cents. Now, if we cared about the amount of interest that was actually earned on this account, what we could do is, in terms of the withdrawals, or how much the student actually gets, 2,500 times 30 withdrawals is going to be 75,000. So the interest, this is how much the account ended up giving. This is how much he actually put in. We subtract them, $32,546.49 in interest, which is pretty awesome. All right, let's try the next one. You've just won the lottery. $1 million is now yours to do with what you like. Being a smart investor, you decide to provide for future you. What monthly income can you give yourself for the next 25 years if you invest the $1 million today at 7.8% compounded monthly? So first of all, I know this is present value because I'm depositing money today, presently, and then I'm going to withdraw from it for the next 25 years. So this time they actually gave you the present value and we're actually looking at those regular withdrawals. So R is unknown, but I know the interest compounded monthly, so 0.078 divided by 12, and that's 0.0065. N, well, we have 25 years and we're compounding monthly, which means we're going to take monthly withdrawals, so 12 times a year. That's 300 withdrawals in total. And I know my present value is $1 million. So I'll start off with my present value formula. I don't plug it in incorrectly. So instead of present value, I will put $1 million. I don't know R, I do know my I, 0.065, so the negative 300 all over 0.0065. Now, just like with the future value scenarios where we were looking for R, I would just put the 1 million over 1 and cross multiply. So 1 million times 0.0065 is 6,500. The rest of it stays the same. I will just simplify 1.0065, take away that addition. And now I just want to get rid of that entire bracket. I'm not going to go to my calculator and write it as a decimal because then I take away from the accuracy. So I'm just going to actually fully divide out the bracket. So it cancels it out on the right, but I know whatever I do to one side, I better do to the other. So there we are. So I recommend pausing the video, trying it in your calculator, and you should get, I'm just going to write my answer here, approximately $7,586.14. And then we'd write a therefore statement, but I have obviously run out of space. So therefore, your monthly income could be $7,586.14, which is pretty awesome. All right, let's go to our final question here. Feeling the need for speed, you decide that you're going to buy a Tesla Roadster. Somehow, you manage to convince a bank to give a teenager with no credit history the $200,000 required to purchase the car. If the bank charges you 6.6% per annum compounded monthly, what will your monthly payments need to be if you're going to pay the car off in 20 years? First of all, I see monthly payments or monthly deposits or withdrawals, whatever you want to call it. So right away, I know it's not regular compound interest. Now I just have to decide, is this future or present value? Think of your loan as the present value. Okay, you presently owe $200,000. Each month, when you make a payment, you're taking away from that loan, you're decreasing it. So because of that action of decreasing the amount that you owe, this loan is an example of a present value annuity. It's just you're not giving this money to yourself, you know, like in the other scenarios, it's money that you're owing. So it is a payment. So we don't know the regular withdrawals or payments. That's what we're looking for. My interest, 6.6% per annum compounded monthly. So 0.066 divided by 12, which is a nice decimal again. If it weren't, I'd keep the fraction. And then we want to pay the car off in 20 years. And 20 years monthly, so 20 times 12, that's 240 payments that you're going to have to make. And we do know the present value. The present value of the loan is $200,000. So it's the exact same as the previous example where you're solving for R. So why don't you go ahead, pause the video, try it out on your own, and for fun, why don't you figure out how much interest you actually paid if you're going to pay this car off in 20 years, which is ridiculous. So pause and try. All right, when we plug stuff in, 200,000 equals R, 1 minus, I'm just going to go to 1.0055 right away, to the power of negative 240, all over 0.0055. Now I'm going to cross multiply here to get 1,100. And then we have this giant bracket that we still have to get rid of. So that's going to be our next step. We're just going to divide it out. And whatever you do to one side, you have to do to the other. And the reason we're doing this division is because we want to cancel it out on the right side so that we are just left with R. So R ends up being approximately $1,502.94. So what this means is that therefore the monthly payments are $1,502.94. And you're making 240 payments. So let's figure out how much you actually end up paying. $240 payments. Each one is $1,502.94. If you plug that into your calculator, this is how much you actually pay for the car. $360,705.60. When the car only originally cost $200,000, which is still a lot, but look at how much interest you had to pay. So for the interest, we would just be subtracting how much you actually paid, subtract the original cost. So you pay, if this were you would have paid $160,705.60 in interest. So obviously, interest rates are pretty high. Like, this is an exaggerated example. You would not pay a car off in 20 years. Although that's an expensive car. But paying something faster is obviously better because interest accumulates so quickly. But there it is. Loans are examples of present value because you start with a present amount and you are making payments to decrease that loan. So you're withdrawing, let's say, from the loan. But that's it for present value. So future is all about building up your account. You're making those deposits, whereas present value, you're putting a lump sum in, or you have a starting loan and you slowly withdraw from it or withdraw from the loan.